So thank you so much to all of you for coming. Um, this is the inaugural annual Ashok Gupta Memorial Lecture in Parkinsonian Disorders. And my name is Deepak Gupta. I'm Mr. Gupta's son. And this event has been hosted by the Binter Center at here UVM Medical Center. So I won't take too much of your time. I hope you have had a chance to read about my father in the handout or brochure which was given, but I would like to take a few minutes to talk about him before we begin to celebrate his legacy with Dr. Fahn giving the inaugural lecture today. So briefly, he was born in 1956 in Kekra village, and to have a more pictorial view, is about 20 kilometers from New Delhi. So who was he? My dad was son of his parents, Mrs. Ramvati Devi and Mr. Sureshchandra Gupta, and brother of three siblings. He actually lost his dad pretty early. I think when he was finishing his college, he lost him. So he overcome quite a lot of obstacles after that. And then he was husband of my mom, Mrs. Sudha Gupta, and he was father of three of us, my older brother Vipin, myself, and my sister Anjali. And then he was father-in-law of our spouses, Sanjeev, Neha, Rashmi. Rashmi is my wife who's sitting here in the auditorium today. And then he was grandfather of six children from three of us. But very briefly, as you saw in the brochure, he did quite a lot of education, and that was always inspiring to me. In 1960s and 70s in India, it wasn't easy, especially he really was born in a village with no resources. So I think he was the only one to go to college from his family. So he took quite a courage to go to these different universities to train himself, and finally became a school teacher, as you read in his brochure. And he was a religious and family man, as I summarized in the brochure. And I think I should say he was a self-made man. He did quite a lot of things from the place he was coming at. He was a dedicated school teacher for over 30 years. And he was a Parkinson's disease patient for over 13 years. And I'm not going to go over his disease, but I hope you had a chance to read about it in the brochure. And I think he was alive for lived over 64 years. And I will just say two more things. I've been asked what was the motivation for me to do this. I think it has been one of the things was he could never come and visit me in States. He was scheduled to come to meet me for the first time before he passed away. So I feel through this annual lecture, he'll be able to visit me every year. And as my patients tell me, he visits them every day. But I think with this, I hope I will never forget him for many years to come. And I think that's pretty much it for me. And at this point, I would like to thank you, Dr. Fahn, for coming. This is, really a big deal for him to come for this inaugural lecture. And he was my mentor in fellowship, but I won't be taking the time to introduce him, and he probably doesn't need an introduction, but I will request Dr. James Boyd, my boss, to introduce him over a few minutes. Thank you.
So thank you all for coming. I think this is really a wonderful tribute to your dad, Deepak, and I'm so glad that we were able to bring it together. And certainly as an inaugural speaker, it's an honor to have Dr. Fahn. For anybody who has trained and has chosen a career in movement disorders, Dr. Fahn's name is one which rolls off the tongue pretty easy. You can't practice movement disorders without having read an innumerable number of his journal publications, his textbook, which is kind of the Bible of movement disorders, taken his course in Aspen, which is a rite of passage for every movement disorder specialist, and also the largest organization for movement disorders research, the Movement Disorder Society. He founded the Parkinson Study Group, which still stands as the largest research group in Parkinson's disease, which he started many years ago and currently lives on. And we fortunately are a site and part of the research that they do. So it would be difficult to overstate his impact on people who care for those with Parkinson's and for the people who have Parkinson's disease in terms of the development of therapeutics and our understanding of the disease. So thank you so much for coming, Dr. Fahn, and pass the mic to you.
Okay, I think I turned this on. Thank you very much. And it's really remarkable, Dr. Gupta, about your honoring your father like this. I don't think I've ever encountered this before. And so obviously a devoted son of your father. And I'm sure he's looking down on this and appreciating what you're doing and pleasing him, no doubt about all this effort you've done. You and your families, not just you alone, but your whole family, putting this foundation together and having this lecture. And I am honored to be the first of the Ashok Gupta lectureship. So my talk is, I guess I have to work on this. Yeah. So I'm going to talk about the history of how we got to Levodopa. And before I do, let me just introduce the fact that, first of all, I have no conflict of interest. Just a little bit about their current therapeutics. Hopefully, we are on the verge of entering the era of neuroprotection using our knowledge on alpha-synuclein, the rogue protein that accumulates and aggregates in Parkinson's disease and causes the progression of the disease. And what led to that was all the genetics. This all began about 30 years or so ago, and it's still in the research phase because we don't have a treatment yet. That's why I said we're anticipating entering the era rather than being in there right now. But the research is in that era. This is what the work is going to be doing. Certainly, right now we are currently in the dopamine era. And as I have on the slide, we can probably date that to the year 1970 when the FDA approved Levodopa for Parkinson's disease. And anyway, it's very likely we're going to remain in the dopamine era, even when we have neuroprotection, because there'll be people who have symptoms of Parkinson's. And it turns out there's no better drug right now than Levodopa, improving the dopamine system in the brain. And although people have been working on other drugs, and there are other drugs, nothing is as good as Levodopa. It remains the gold standard, or probably will remain the gold standard of symptomatic motor symptoms of Parkinson's disease. So what I want to talk about is how did we arrive at Levodopa? Now, it seems for those who are new to this field, it's cut and dry, it's a slam dunk. When striatal dopamine deficiency was discovered in the brains of people who died with Parkinson's disease, the natural thing was just give the precursor to dopamine, restore dopamine, and the precursor is levodopa. And certainly that was tried. That was the obvious thing. And this is what everybody believes it was straightforward, but it wasn't straightforward. The early investigators did have this idea, and they did give some IV and some oral levodopa. But it didn't work, or at best they had a transient improvement, mild improvement, didn't last long, maybe a couple of hours. And so it was more or less a failure in that sense. And what eventually happened is a new investigator came along who had a different idea of what was causing the symptoms of Parkinson's disease. He tried different agents to improve that symptom. This is the story I'm going to tell you about. And he included L-Dopa in his trial, and he knew how to give L-Dopa, and he got it to work, and that's how he restored dopamine. And he agreed ultimately that that was probably the mechanism that's restoring dopamine, but he didn't think so when he started. And so I'm going to tell you this interesting story and how this was almost missed. In other words, the people who had the right idea didn't have the right method to get the right treatment. But the guy who had the wrong idea, he used the correct method, and then he got to the right answer. So this is the story. Now, I used the date 1970, but actually the very first paper on high dosage levodopa that was truly effective was really in 1967. So we can even go back to a little longer than 52 years. to say the dopamine, the L-Dopa story started. As I mentioned, this still is the most potent and important drug for motor treatments of Parkinson's disease. There was no antecedent. It was not an evolutionary drug. It wasn't something else led to this from previous drugs. This is brand new idea, new concept. So therefore it was revolutionary. And I fortunately lived long enough to have been in that era. I was a resident, I finished my residency, I guess, and I was just a young faculty member when all this began. And when L-Dopa came into patients' mouths in order to get them better, they were getting out of the wheelchair and walking. This was really, truly remarkable. And yet it was almost missed because they didn't know how to use it right. And we might not have had it. So this is that story. And what was treatment of Parkinson's like then before L-Dopa? I was a resident beginning in 1959 in neurology, and in the 50s and 60s, the standard treatment is what you see here. We used drugs called anticholinergics. I listed the two most common ones at the time, but there are many anticholinergics. They probably all did the same thing. They affected but there was a lot of side effects, and they only had modest improvement. People would estimate maybe 30% improvement of their motor symptoms from these drugs, but it was definitely something. We also had physical therapy. We still have physical therapy. Physical therapy remains important because people do better. They have physical therapy. And in the 1950s, there was stereotactic thalamic surgery. This is before the current DBS, deep brain stimulation surgery we have today. Here they actually made lesions, and the big pioneer was Irving Cooper. And you see his picture here. And you see on this slide, if you look at the very bottom right of the Life magazine, June 1959, this is an article about L-Dopa surgical treatment from Irving Cooper. It says, Miss Burke White fights against crippling disease. Well, Margaret Burke White, I don't know if there's some gray hairs who might remember Margaret Burke White. She was a very famous newspaper reporter, war zones and everything else. And she developed Parkinson's disease. And she was going to, this picture is not Margaret Burke White on the cover. This is obviously the Air Force Academy graduating his first class. But this is Margaret Burke White on the your far right. And Irving Cooper with his assistant is there talking to her. And she's going to undergo this deep brain stimulation. This not deep brain stimulation, thalamic surgery, making a lesion in the brain and the thalamus. It mostly helps the tremor. It did help a few other symptoms, but it also had side effects that tend to involve your speech. You get dysarthria. And people were really not going back to work. They might have had less tremor, but really wasn't a great answer. But nevertheless, that was the major treatment. A lot of famous people around the world got the surgery. Irving Cooper became very well known. He had honorary degrees from most universities in the world. I went to his office once, and 4 walls were filled with plaques of honorary degrees and memberships in societies of all these international societies. He was well famous in his time. And but again, it didn't really solve the problem for Parkinson's disease. So how do we get from that state in the 1950s and early 60s to where we are today? And we can start this story with how chemists and pharmacologists synthesize dopamine. This was 1910, so we're talking over a century ago. Simultaneously in London were Barger and Ewans at the Wellcome Clinic and labs in London synthesized dopamine. And then simultaneously in Berlin and the Pharmaceutical Institute there, Monica Jacobson did it from a different precursor to start with. And they both got dopamine. And they didn't know what it was. Barger teamed up with Henry Dale, later Sir Henry Dale, and even later Nobel laureate Henry Dale. And they tested the pharmacology of this and said it was a weak sympathomimetic epinephrine-like drug. It's interesting, Dale, years later, 1952, gave the name dopamine to her, or at least supported it. There was The name of this compound was by its chemical name, 3,4-dihydroxyphenylethylamine. It's a mouthful to say, of course. So they shortened it to give its alternative name, 3-hydroxytyramine. And that was the name was usually published in the literature. Some pharmacologists were pushing for changing it to dopamine, and Dale finally came around to this and supported it, and that's the name ever since. And his justification was, well, this compound was more closely related to dopa than it is to tyramine, so let's call it dopamine, and that's the name is stuck. But the early literature also always had it by 3-hydroxytyramine or dihydroxyphenylethylamine. Now, a year after the isolated dopamine or found dopamine, and chemically Casimir Funk synthesized L-Dopa. He was in London at the Lister Institute, and these are the chemical structures: L-Dopa on your left and dopamine on your right. You see just the carboxyl group is missing from dopa, and it becomes an amine, dopamine. So L-Dopa is an amino acid, and dopamine is an amine. It's a charged compound. It itself can't enter the brain, dopamine, but L-Dopa can. Well, you say, who's Casimir Funk? I mean, preparing for this kind of a lecture, I had to look up these people, and it was amazing. First of all, his name, as you can tell, is from Polish. He was born in Poland. He was a Polish scientist, and he died in New York. But his higher education was in Germany. And then later he moved to London and went to the Lister Institute, and that's where he synthesized dopa. He had always planned to determine what does L-Dopa do pharmacologically, but he never got the chance. The Lister Institute at that time was very much concerned about beriberi. It was going around the world. What was causing beriberi? That was a big problem, and they wanted they put him to work to find out. And it was Funk who found that it was the deficiency of niacin, which is vitamin B3. And Funk later came up with the name vitamin. He used that term for vital amine. So he shortened it to vitamin. So he's the one who invented that name, vitamin. World War I started in 1914 in Europe. He moved, I guess, many job offers in the United States. He moved to the United States, worked in New Jersey, and he looked for other vitamins, and he discovered B1, thiamine, B2, riboflavin, C, ascorbic acid, and vitamin D. After his death, the Polish Institute of Arts and Sciences of America give an award annually to pick a Polish-American scientist and give him the Casimir Funk Award. And that still exists today. Back to the story. So after Funk isolated L-Dopa, Marcus Guggenheim, a pharmacologist in Switzerland at Hoffmann-La-Roche, isolated L-Dopa from the fava bean. It turns out L-Dopa is only found in nature in a couple of beans, the velvet bean, the fava bean. And as a true pharmacologist, he tested it. What does it do? So he took 2.5 grams himself, good pharmacologist, and immediately vomited. And he studied his urine. He added stuff to it, and he found that when he added alkali, it turned black. Well, now we know that this is oxidized L-Dopa and dopamine when it got into alkali. Guggenheim went on and a very successful career at Hoffmann-La-Roche, and he actually coined the term biogenic amines ultimately. But then there was not much interest and not much activity in dopa or dopamine in the rest of that decade in the 1920s. But by the 30s, there was a lot of interest now, certainly by endocrinologists, about epinephrine and norepinephrine. And so there was more interest now in dopamine. They're thinking maybe L-Dopa and dopamine are precursors to norepinephrine and epinephrine. In the late 30s, Hermann Paschko, a German Jewish refugee trained in Germany, got out when Hitler and the Nazis came to power, went to Cambridge. He discovered the enzyme monoamine oxidase, which degrades all the catecholamines, norepinephrine, epinephrine, and dopamine, for example. And he thought that was how it these neurotransmitters would be deactivated, like acetylcholine is deactivated by cholinesterase. It turns out not to be the case. And in fact, the guy who discovered that was deactivated, got the Nobel Prize. I'll come back to that in my story also. In Germany, in Rostock, Germany, again, just before the war, World War II, the enzyme dopa-decarboxylase was discovered by Peter Holtz. And that converts dopa to dopamine. And as you can see in the next slide, where I have it circled, you can see dopa going to dopamine. And then if you look, keep going down straight on that arrow down, the monoamine oxidase was one of the enzymes that catabolizes. There are other pathways, we won't go into that. But anyway, so this pathway was now known. In N39, Holtz found that, and simultaneously Bashko independently supported the idea that L-Dopa and going to dopamine is the precursor and or metabolic intermediates, in other words, to norepinephrine and norepinephrine. They were not substances in their own right; they were just intermediaries, and didn't have any substance on its own doing anything. And that was the way it was. This we're now going into World War II. Peter Holtz was still in Germany, and he continued to work on dopamine there. By the end of the war, in Sweden, Wolfgang Euler, who was working on norepinephrine, he found that it was the neurotransmitter for the sympathetic nerve endings. It was a big event, and he shared the Nobel Prize in 1970 with Bernard Katz from England, who had discovered that acetylcholine was the neurotransmitter for the motor neuron. And it was Julius Satsang who discovered many of the metabolic pathways for norepinephrine and how the neurotransmitter effect was terminated. It was not through monoamine oxidase, it was reuptake mechanism. He discovered the reuptake mechanism for the catechol, all the amines to get back into the synapse, presynaptic vesicles. And that's how it was terminated. And anyway, the three of them shared the Nobel Prize. And by the 1950s, people were discovering small amounts of dopamine in tissues, now, therefore suspecting maybe it's not just an intermediate, maybe there's some substance to it itself. By 52, Holtz showed that the cofactor for dopa-decarboxylase, which is the enzyme he discovered, was pyridoxal phosphate. And this becomes important to the story. Also, pyridoxine is vitamin B6. And it's the cofactor to convert dopa to dopamine through dopa-decarboxylase. Now, Blaschko, Armin Blaschko, moved Cambridge to Oxford, and he found that at least in the adrenal gland, the epinephrine there was bound to granules, and that led to the way to thinking, eventually discovering that norepinephrine and it turns out dopamine as well, and nerve terminals are in synaptic vesicles in the nerve terminals. So they're in granules. They're supported there and out of arm's way from other enzyme activity working on them. Now, at this point in time in our story, we have to introduce Oleg Hornikevich. Because in 1956, he got a postdoctoral fellow and went to Oxford on a fellowship and went to Blaschko's lab. Blaschko assigned him to work on dopamine, what's dopamine's effect on blood pressure. He did that project. He showed that it was dopamine and not some other metabolite from dopamine that had some effect on blood pressure. And you see it was published in 1958 at the bottom of the screen here in yellow. So who was Oleg Hornikevich? Because he's one of the stars in the story. Well, he was born in 1926 in Sikhiv, which is really a suburb of Lviv. Now, everybody's heard of Lviv in the last few days. Lviv is in western Ukraine. It's been relatively safe from the war up to now. Its airport was bombed, of course. In those days, it was part of Poland. Before World War II, this area, western Ukraine, was eastern Poland. So he was really Polish in that sense. And he was the youngest of three boys, and fourth generation of Catholic priests. Now, you can ask, how does Catholic priests have sons? How do they get married? It turns out this is an interesting history. You learn a lot when you start doing this kind of work. It turns out that in Ukraine, Eastern Orthodox was the competing religion, the Catholicism, and Eastern Orthodox priests can marry and have children. So the Catholic Church made an exception for the Catholic priests in Ukraine. They can also marry and have children. So that was how Hornikevich was born. Everybody knows what happened in August 1939, the infamous Ribbentrop-Molotov Pact. The two foreign ministers for Germany and Soviet Union, respectively, signed a non-aggression pact which took the world by amazement. Nobody expected that, and that was the forerunner for dividing up Poland. So if Germany was going to invade Poland, they didn't want Russia, the Soviet Union, to come and fight them. So they made this pact, so Nazi Germany was able to invade Poland September 1st, and they took the western half of Poland, and Russia came in and took the eastern half, and they divided up Poland. Again, Lviv was the eastern half of Poland in those days, and the Hornikevich family was trapped in the Soviet Union. They got out because Hornikevich's mother had Austrian family inheritance, and so they able to move to Vienna during the war. They stayed in Vienna during the war. Eventually, after the war, he went to medical school at the University of Vienna, got his medical degree, but immediately went into pharmacology. He never practiced medicine. And he was working in something, I'm not sure what at that time, but he got his scholarship to go work to study with Blaschko in Oxford. And that's how he got introduced to this. And as you can see in this picture on the left is Herman Blaschko. On the left with the gray hair and only Hornikevich. This is a time when Hornikevich was already famous. His lab at the University of Vienna was enlarged, a brand new lab, and he had a big party celebrating his lab opening and invited Herman Blaschko as his guest. Hornikevich, when I was visiting him, sent me this autobiography of himself, explaining how he got involved in the story, and I had invited him to be a principal speaker at the First World Parkinson Congress in 2006 in Washington. So he wrote this handwritten note for me. He eventually died a couple of years ago, and this is obituary in the New York Times, as you can see here. Okay, so let's complete the story. So how does the body get L-Dopa? I mean, it's not in the diet. A couple of beings have it, but nobody gets their, not like other amino acids you get in your diet. So L-Dopa had to be generated in the body. And so the obvious first thought was maybe tyrosinase. Tyrosinase was an enzyme that was known. It is the enzyme that converts tyrosine to dopa and dopa to dopamine, all in a couple of steps. And that becomes the precursor for skin melanin, hair melanin, eye melanin. So this is a melanin precursor enzyme, but there's no tyrosinase in the brain. So it was looked for. So there's still a mystery. Where does the nervous system get its dopa? And it turned out many labs were investigating this. And the one that found it was Sidney Uniform's lab at the National Institute of Health. It was actually in the Heart Institute there. In the Heart Institute, people were interested in norepinephrine, vital for blood pressure and heart regulation. And one of their postdocs, Toshiharu Nagatsu from Tokyo, was assigned the task of finding the enzyme that was responsible for causing tyrosine to go to dopa in the brain and in the heart. And it turns out they did. It turned out to be tyrosine hydroxylase as the enzyme, published in the JBC in 1964. Now, as an aside, Nagatsu comes back into a movement disorder story. You can see he's the last name on the bottom section here of a paper with the first author, one of his postdocs, Ichinos. They discovered the gene that causes dopa responsive dystonia, DRD. And the gene was GTP cyclohydrolase. And in this slide shows the first step, number one, is GTP cyclohydrolase 1. That was the first step. And what was known was that the cofactor for tyrosine hydroxylase was tetrahydrobiopterin. How do you get tetrahydrobiopterin? There's a sequence of 3 enzymatic steps to get it. And the first step was GTP cyclohydrolase. Well, Nagatsu back in Tokyo was working on his enzyme and these cofactors and what was synthesizing this. And in our lab at Columbia, 2 neurologists, Toby Nygaard and Kirk Williamson, both post-fellows of mine with their labs, they were looking for the gene for dopa-responsive dystonia. Toby Nygaard was very involved. He had collected a lot of patients with dopa-responsive dystonia. And that disease, by the way, was first described in Japan. So they had patients in Japan with that disease. When Toby Nygaard and Kirk Williamson found that the gene location was, I'm going to go back to see, make sure I'm got it right, with 14, chromosome 14q22.2. That was the location, and Nagatsu recognized that's where the gene location is for GTP cyclohydrolase 1. So they immediately got a hold of, as you can see here, Sagawa and Nomura, who had all the patients with hereditary progressive dystonia with marked diurnal fluctuation. That was the name Sagawa gave to this disease, and they had all these patients. So he got blood from these patients. And they found the gene right away. And Toby Nygaard and Kirk Williamson were left in the dust. They found the location, but not the gene itself. And they didn't. Nagatsu was ahead of the game on that. So as I say, he's very important in the field of movement disorders as well. Okay, so we now have the sequence: tyrosine, the dopa, the dopamine, and the nervous system. Now we're going to turn our attention. How did dopamine then become associated with Parkinson's disease? Now that we finished with the basic science. And here the story starts in India, where Dr. Gupta was born. Indian pharmacologists and practitioners had discovered that the plant leaves and the roots of a plant called Rauwolfia serpentina, when crushed up and given to people, it calmed them down and controlled their blood pressure. It lowered blood pressure. And up to that time, in the 1950s, before the 1950s, there was no treatment for high blood pressure. And I remember as a medical student, I became a medical student in the late 1950s, graduated in 58. And I still remember when a malignant hypertensive person came into the hospital, over 200, they thought he was going to have a cerebral hemorrhage. Reserpine was available. They gave reserpine. So they got reserpine by a Swiss pharmacologist in the pharmaceutical industry in Switzerland, began to find out what was in Rauwolfia serpentina plant that allowed this. And they found many compounds, but the most active one was reserpine. So reserpine was isolated, marketed, went around the world with a very valuable drug. And that was the first drug for controlling high blood pressure. It's not even used anymore. And it was also used for its sedating quality. It calmed people down. It was used for people who were overexcited, psychotic, and it eventually used. It was called a neuroleptic because the French psychiatrists were using reserpine and using other drugs that were being developed there, Thorazine in particular. And they were both doing the same thing. They were calming people down, but also causing drug-induced Parkinsonism. And they coined the term neuroleptic for a drug that can calm people down and cause drug-induced Parkinsonism. And there was a lot of interest. What was it in this compound reserpine that causes this drop in blood pressure and also drug-induced Parkinsonism? And the winner of that story was Bernard Brody at NIH. His lab was a famous lab in what's called chemical pharmacology. I'm going to tell you his story in a minute, but he began to work on it at NIH, and he discovered that reserpine releases and depletes serotonin in the brain and in the heart. He thought this was that's the cause of the sedative effect, the depletion of serotonin. And this paper was published by Fletcher, Shore, and Brody in 1955. Now, Alfred Fletcher was a very promising upcoming pharmacologist working at Hoffmann La Roche in Switzerland. And he was sent to Brody's lab for postdoc training, and he was the senior author in this paper. And Shore was a lab tech with Brody in the lab. In the lab also was Julius Satsang, but he didn't work on this paper because, as I'll show you in a minute, he took a sabbatical for a year during this period of time to get his own PhD. Anyway, about Bernard Brody, I mean, again, probably nobody's heard of him in this room, and you have to read about him, but he is considered the founder of modern biochemical pharmacology. He was born in Liverpool, but university educated in McGill in Montreal, and then he got his PhD at NYU in New York. He joined the faculty at NYU. They gave him a lab at Goldwater Memorial Hospital. If anybody knows New York City, it's on one of the islands in the East River. And he had his lab. One of his pioneering works, he showed that animals and humans didn't differ the way they metabolize drugs. That was a significant factor in drug metabolism in those days. And he also developed a method for treating malaria. In 1946, he hired Julius Satsang. As I said, he went on to get the Nobel Prize, Julius. And they worked together on non-aspirin analgesics. At that time, one of them was causing hemoglobinemia, and they found that its metabolite was acetaminophen and did not cause hemoglobinemia. And acetaminophen was marketed, became Tylenol, a very popular drug even to this day. And they were famous for that. And anyway, Brody was recruited by NIH. They were looking to get biochemical pharmacology at NIH, and especially the Heart Institute. He went to the Heart Institute, got his lab going in 1949, and he began to work on norepinephrine and the catecholamines in the lab, and that's when they discovered this. He was famous. Brody was famous in his day. He won the Lasker Award in 1967, and he won the National Medal. He was given the National Medal of Science in 1969 for all of his work. Just as an aside, I'll tell you a little story about Julius Satsang. He was a New York City boy, poor family. He could not get into medical school. He was turned down by all the schools he applied to. Of course, he went on to win the Nobel Prize, but anyway, medical schools knew better, I guess. But he wanted to be a physician, but he couldn't be, so he became a lab tech. He graduated from City College of New York, no tuition. Became a lab tech at NYU. He wanted to get ahead. He went to night school, got his master's degree at NYU, working, taking classes at night. And then he worked for the New York City, doing assays about enzymes and other things. Eventually, Bernard Brody hires him. And in 1946, he worked, I told you about the work on Tylenol at that time. They worked, and he took Axelrod with him to NIH. And many works done in caffeine, codeine, morphine, so forth. As you see here on this slide, many things. He also discovered the enzyme catechol-methyltransferase, which degrades catecholamines, and the mechanism of reuptake on this. So he shared the Nobel Prize after Rod. But in 1954, he took a leave of absence. He was the chief lab tech for Brody, but he couldn't get his own lab. He didn't have a PhD, so he took a leave of absence. He got his PhD. In 1 year, he was able to get his PhD at George Washington University. He had all these scientific papers. Then he came back to NIH. They made him a section chief. And when I went to NIH, he was the section chief. And a lot of young guys picked their postdocs at NIH in those days with him. He was a very famous scientist in his day. Anyway, as I said, he got the Nobel Prize. He shared it in 1970. Okay, well, so here is Brody's lab. He just discovered the serotonin depletion effect. And Arvid Carlson now comes into the picture. Arvid Carlson comes a postdoc in Brody's lab. He was a Swedish, I'll tell you his story in a minute, but he wanted to do biochemical pharmacology training. So he was suggested to go to Brody. He got 6 months in Brody. Brody, meantime, was working already on this reserpine effect. So when Carlson arrived, Brody assigned him, okay, we found what happens with serotonin in the brain and heart. Why don't you work on platelets? So he was assigned, what does reserpine do to platelets, serotonin? And it shows it depletes in this and platelets as well as in these other tissues. Carlson suggested to Brody, why don't you look at other amines besides serotonin? Why just Brody said, no, serotonin is it. We're not going to have to look any further. So Carlson always had in the back of his mind, well, maybe reserpine is doing something more than just serotonin depletion. So after his fellowship, well, let me tell you about his story. He was born a couple of years after Hornikavich, or it was a couple of years before Hornikavich in Sweden. His father was a historian, a professor at Lund University. Harvard was educated there. In World War II, he had to serve in the military. Sweden, as you remember, was a neutral country like Switzerland in World War II. And like Switzerland, they had a standing army to defend its borders. So everybody had to serve in the army there. He served in his army. But after the war, he went to medical school at Lund University, got his MD the same year as Hornikavich in Vienna. Again, he didn't go do any practice in medicine. He went right into pharmacology. He wanted to go into pharmacology, and he began to work on calcium and vitamin D. But he was interested in biochemical pharmacology, as I mentioned before, and colleagues at Lund told him, well, if you really want to do this, you have to go to Brody's lab and learn how to do it. So that's why he went to Brody, and it was Brody that he learned about the amines. And he took that back with him. He got this idea that, well, let's study what does reserpine do to other amines besides serotonin. So he goes back to Sweden. He has his own lab now. But by that time, a group from Edinburgh already found that reserpine releases norepinephrine in the central nervous system. But Sweden teamed up with Hillar. Hillar was a well-established histochemist in Lund University. And he developed eventually the fluorescent histochemical technique, which becomes so important in our story. Anyway, they teamed up and they found that reserpine does release and depletes norepinephrine from the adrenal gland. Hillar was interested in the adrenal gland. Meantime, Carlson started his own research, and with his couple of technicians, they did this very famous, simple experiment, elegant but simple. Carlson took rabbits. He gave them reserpine, as you see in the upper picture. These rabbits got flaked out. They couldn't move. Their ears are floppy. They're just lying on the ground, unable to move. They have drug-induced Parkinson's. He gives them the precursor of serotonin, 5-hydroxytryptophan, and nothing happened. He gives them the precursor of catecholamines, L-Dopa, and bingo. Look at the bottom picture. The rabbits woke up. Ears pop up. They had an awakening experience. Carlson writes this up. It's less than 1 page long. This is his paper. It's in Nature. This is the top half of the page. As you see, if you look at the reference page 180, well, you think it's an abstract. It's a single page paper. It goes down the length of the left-hand column. It comes up the right-hand column, goes down a little over about halfway. So it's a little over a column in length. And he writes this paper. He also submitted this picture to the Nature. This is published. Nature editors, reviewers accepted the paper. Yes, they didn't have any hesitation, but they didn't accept the picture. The argument was, well, we don't need the picture. The paper, the text says it all. You don't need the picture. So the picture was never published until he wrote his Nobel Prize winning article in the book for the Nobel Prize winners. And this picture was published with his Nobel Prize. So it was a simple experiment and elegantly done, and led to the idea that it was catecholamines and not serotonin that was important for this sedating or drug-induced Parkinson's effect. In the meantime, back in England, Kathleen Montague found some dopamine in the brain, but Carlson went on and developed a new fluorescent analytical technique to measure very low levels of dopamine in tissue, and use that tissue map dopamine in the brain. He showed that if you give reserpine to animals, it depletes brain dopamine. If you give L-Dopa to those animals, restores brain dopamine. So it showed the rapid effect of biochemistry of it. And people in his lab began to map out where dopamine was in the brain. It was high in the striatum. And by 1958, at the International Symposium for Dopamine, which is about every 2 or 3 years, he reported about his dopamine work and experiments. And he said in that paper that this most likely dopamine is related somehow to Parkinson's. And these are the graduate students of the lab, Burton and Rosengren. They took dog brain and they mapped out the distribution of dopamine in the brain, high in the striatum. But simultaneously, in the same year, published in the same year, Osamu Sano, a neurologist in Tokyo, in Japan, I don't know if he was Tokyo then, also did this in a human brain, postmortem human brain, published in the BBA in 1959, saying the same thing, high dopamine levels in the striatum. In 1959, Carlson published his review, and you can see here, this is his paper showing the distribution of catecholamines in the nervous system, and talked about dopamine and talked about possible Parkinsonism relationship. He died 4 years ago. This is his New York Times obituary. This is hugging his wife when he got the news of his Nobel Prize in 1970. Well, Hornikevich, in the meantime, finished his training with Blaschko. He goes back to Vienna. He has his laboratory at the university there. He's still interested in dopamine. He was assigned that by Blaschko. He read Carlson's articles about the rabbits experiments, about the assay for dopamine that was low. And he wondered, why doesn't Carlson measured dopamine in human brains with Parkinson's? And he said, well, if he's not doing it, I'm going to do it. He collected brains, and in Austria, brains are available for autopsies unless the family rejects it. But in other words, it's automatic, more or less, in Austria. So he was able to collect these brains. He got post-encephalitic Parkinson brains. He got Parkinson's disease brains, and he measures dopamine. He finds that dopamine is depleted in the brain of both PD, Parkinson's disease, and in post-encephalitic Parkinsonism, and publishes it in German literature, Clinical Wochenschrift, in December 1960. It was widely read by that time. People knew about this paper and found it was a very important paper. Hornikevich continued to work on brain dopamine levels. He eventually found it was also deficient in the substantia nigra. His paper, the 1960 paper, was ultimately about 30 years later. So translated into English. So if you want to read his paper in English, you can. It was in this journal, Parkinson-related diseases. Ehringer was his lab tech. The reason his name was first is because the rule of the pharmacology department in University of Vienna was that it has to be alphabetical order. And of course, you can guess from that rule that the chairman of the department's first letter starts, his name starts the letter B. Anyway, Ehringer and Hornikevich's paper was this one here. Hornikevich writes his own review, pharmacological reviews, and titled Dopamine, 3-hydroxytyramine, and Brain Function. And he showed in this paper from all of his studies of brain tissues of people with Parkinson's that the more severe the Parkinson's, the greater the dopamine loss in the striatum. So there's a correlation of the amount of dopamine loss and the amount of symptoms the person has. So it's a direct correlation. And this is that paper. Okay. Now we have a biochemical basis for Parkinson's disease, but the pathology of Parkinson's has nothing to do with the striatum. The Parkinson's disease cell loss was in the substantia nigra. In those days, in 1950s and 60s, they didn't know any connection between the nigra and the striatum. The neuroanatomy books didn't have it. They looked for it. They didn't find no techniques. So how did this tie together, the pathology and the biochemistry? Well, there are two things. The Hillarp method of fluorescence histochemistry in Sweden had a way to highlight the catecholamine neurons and the serotonin neurons in brain. And the second way was a combination of the neuroanatomy and biochemistry. And this was done This papers here was from Hillarp's group, Alstrom and Fuchsa and Andem were postdocs. They wrote these papers, and they showed they can see in histochemistry this technique, the dopamine neurons rise in the substantia nigra and move up to the striatum. And they found norepinephrine cells and serotonin cells also going to other places in the brain, but also originate in the brainstem. And in Montreal, the francophone Louis Poirier at the University of Montreal, a French-speaking university, a neuroanatomist, teamed up with Ted Sorks, Anglophone biochemist from McGill University, English-speaking university in Montreal. They teamed up. Poirier got some non-human primates, made lesions of substantia nigra of different sizes, dissected out the striatum, gave it to Ted Sorks, who measured dopamine, and show again, the bigger the lesion, the greater the loss of dopamine in the striatum. So we tied up this picture now of substantia nigra dopamine cells going to the striatum. Okay, let's turn our attention now, connecting DOPA with Parkinson's and humans using it. Well, it actually really starts with drug-induced Parkinsonism. Rudolf Deggertz was a psychiatrist in Frankfurt, in Germany, treating people with psychosis with reserpine in the 1950s. And he read Carlson's paper, the rabbit experiment, and he said, well, let's try L-Dopa in our patients with drug-induced Parkinsonism. They got Boehringer and Son, German pharmaceutical company, to make some L-Dopa for them. They boiled some water to purify it and sterilize it, that is, let it cool to 80 degrees centigrade, added L-Dopa, and gave different concentrations mixed to patients. Starting out with 50 milligrams IV, and they built it up in increments. By the time they reached 270 milligrams, patients felt ill. By 350, all patients were vomiting. But they did report transient reduction of the sedation effect, what we would call post drug-induced Parkinsonism. So the patients were talkative, animated, moving about. They tried various combinations with hormone oxidase inhibitors. They tried drug-induced chlorpromazine and so forth. So they tried all kinds of things. And so this technique was being done by Deggertz. And this is the paper that's published here. It turns out Sano in Japan had the similar idea. He was aware of the Carlson effect too. And as I told you, in 1959, he published his paper about dopamine distribution in the human brain. So he decided to test L-Dopa in patients with Parkinson's disease, not drug-induced Parkinson's, but Parkinson's disease. He injected 200 milligrams IV. He saw there was less rigidity and tremor for a few minutes, but no better than trihexyphenidyl, which is, of course, the generic name for Artane. He reported this in a symposium in February 1960. Remember, Hornikavich and Ehringer's paper was in December 1960, so this was before that. They published this, and it was only an abstract. It was in Japanese. It was not even a full paper. He also reported in that abstract that he looked at the brain of a Parkinson patient, and he showed it was depleted in the nigra and the putamen dopamine, but he didn't seem to go anywhere with it. He thought that this drug doesn't do anything. It was no better than Artane. So he never went further with this. The guy who was really brilliant, I'm not to say the others aren't brilliant, but Patrick McGeer. Patrick McGeer was a neuropharmacologist at the University of British Columbia in Vancouver. He was aware of the Carlson paper too, and so he published this paper in 1961. He began work in 1960. This is before Hornikavich published his paper. He began work. He decided he would use L-Dopa orally in high doses. He suspended it in methylcellulose, and he gave it to drug-induced Parkinson patients. 3 of those patients had reserpine-induced Parkinson's. The others had phenothiazine-induced. But he was a true scientist. He did a double-blind experiment. He gave diphenhydramine, massive amounts, 400 to 600 milligrams a day. I've never used more than 100 milligrams a day. Anyway, this was the standard dose he was using, and he got a better anti-Parkinson effect with diphenhydramine as Benadryl. It was superior to what he found in the L-Dopa. And this is drug-induced Parkinson. And the phenothiazine, of course, had no effect because it's a different mechanism of resurfacing. But in this paper, which was a negative paper, he gave all of it. He was so smart, he gave them all paradoxine. He wanted to encourage dopa to dopamine. What he didn't realize, which was later found years later by clinical neurologists, that when you give paradoxine to L-Dopa, when you treat L-Dopa in patients without carbidopa, you lose the dopa effect because the dopa gets converted peripherally circulated to dopamine. Not enough gets into the brain. And that may be one reason why he failed. It was too smart, perhaps. Anyway, it was a failed paper. He does mention Carlson, mentioned Sano's work, Degrich's work. So he did all that. He doesn't mention Hornikevich's. Again, Hornikevich's paper probably came out in December 60, after he already did his work. And this paper was published in JAMA in 1961. Well, of course, once Hornikevich and Ehringer found dopamine deficiency, they knew what to do. They were going to use L-Dopa to treat Parkinson's disease patients. So he's an MD, Hornikevich, but he's not practicing, he has no license. He teamed up with Walter Birkmeyer, who's a geriatrician in Vienna, who had many of the Parkinson patients under his hands. And he encouraged Birkmeyer to team up with him. Birkmeyer was much more interested in serotonin than dopamine, but Hornikevich convinced him, look, I got some L-Dopa left over from Blaschko's lab. Let's try it in some patients. So they gave injections. They did the same technique that Beckwith did, boil water, sterilize it, cool it down a little bit, add dopa to it, and they gave injections. And they did report a benefit, a transient benefit, and it lasted for just a few hours. And this is the paper. Again, it got published about 30 years later in English, the same journal, translated into English, but it was published in German. And here is a picture of Hornikevich and Birkmeyer later in 1970. Well, many other people were also beginning to try D-L-Dopa. Andre Barbeau was one of the first in Montreal. He gave up to 200 milligrams. He was saying some benefit. Others reporting benefit too, as you see their names under here. Friedhoff was a psychiatrist in Mount Sinai in New York, Umbach and Baumann in Germany, so forth, from Italy, other parts of Europe. All tried it. They were reporting some slight benefit with small doses of oral or IV dopa, but simultaneously failed to find any benefit. Mel Greer at University of Florida and tried it in 2 patients, up to a gram of D-L-Dopa orally, found no benefit. In Italy, Rinaldi, even the presence of an amine oxidase inhibitor, found no benefit, failing in Germany, double blind, so forth. People in Finland and Renee and Sonainen, they could not find any benefit from L-Dopa. And this is now into the 1960s. And McGear, again, didn't give up. Remember, he did the dopa drug-induced Parkinsonism. This time he tried now in Parkinson's disease. He teamed up with a neurologist in Vancouver. Forgot her first name, Zeldowitz. I met her once, but Patrick and Zeldowitz teamed up, gave 10 patients, her patients, up to 5 grams per day of D-L-Dopa. This is a high enough dose that should work. But they only gave them for several days. One patient, they did give 3 grams a day for 3 years. Now, why did that fail? It should have worked. So one makes me think that maybe this was a atypical Parkinson's. It wasn't really Parkinson's, like that's a supranuclear palsy, which doesn't respond to L-Dopa. So it's possible that's the reason he failed. Another possibility I thought was maybe he used pyridoxine again, but it doesn't say in his paper whether he used it or not. It didn't say he didn't use it. It didn't say he used it. So we don't know if he did or didn't. But anyway, he did fail. This was reported in the Canadian Journal of Neurology, and this is that paper. And again, fair enough high doses. And so this was a failure, and this was published in what year was this again? 1964. So he concluded that dopa has little to offer as a therapeutic agent in the treatment of Parkinson's disease. In 1965, Roger Duozan at Mount Sinai published a big review on the therapy availability for Parkinson's disease. And he did talk about dopa. He said dopa effect is in any way rather no different than any mild symptomatic amine. It wasn't really doing anything. In 1965, there was an international symposium at Columbia. Melior was the chief organizer of that. I had just joined the faculty in September that year. This was in November. So I was came from NIH, and I was hired by YARDA into one of these labs at Columbia. I was still working on sodium ATPase, the electric organ of the electric eel. But I went to this symposium. Carlson spoke at the symposium, and then Fuchs and so forth. Hornikavich spoke. And I heard Hornikavich talk. Hornikavich described his work with depletion of dopamine in the brains of people with Parkinson's disease. I was not aware of that. And this was 4 years, almost 5 years after he published it, but I didn't know this paper before. I wasn't in that field. But I got so interested in this that I decided to switch my lab work to the biochemistry of the basal ganglia. And that's when I've been on that ever since. But in this symposium, and this is the title of the symposium, was published a year later. And this is Hornikavich's paper. And in this paper, he says, that yes, L-Dopa seems to work, but it's not the right drug. We can't get it to really work. And although the idea may be right, we just don't have it right. So there's a lot of pessimism. Certainly by the mid-1960s with McGear's paper, the Hornikavich report, Roger Duozan's paper, there was a lot of pessimism. Dopa was going nowhere. It didn't look like I had much promise. Everybody's still doing either stereotactic surgery or anticholinergic therapy. And then comes along George Kotches. Now, who's George Kotches? He was born around the same time, a little older than Hornikavich and Carlson. He was born in 1918. He's Greek. He was born on the island of Crete. His father and grandfather were politicians in Greece. In fact, ultimately, his father became mayor of Athens twice. And the first one was before World War II. And when the opposition, he was lost in the competing race. After that, he left Greece, left Athens and went back to Crete. Anyway, they were there when World War II started, and when the Nazi Germany invaded Greece, they escaped from Greece and went to the United States. He had already started medical school at the University of Athens, but with his parents, he went to the United States. He wanted to become a doctor. He applied to many medical schools, and like Julius Satsang, he was not accepted. Somebody said, "Why don't you just try the best?" So he said, "Okay, I'll apply to Harvard." He goes to Harvard, and his interviewer was a German Jewish refugee from Nazi Germany. He took sympathy on Karl Kotches. He said, "Okay, we're going to take you. You don't even need to take the first 2 years of basic science. You had enough. We'll go right to clinical medicine the third year of medical school." So he went to Harvard Medical School, graduated at Harvard, got a residency in pathology and neurology and Mass General. But he, again, like Carlson and Hornikavich, he did not practice medicine. He went right to pharmacology. He got a postdoc with Van Slyke and Dole at Rockefeller Institute, working on I forgot what the substance, some neurotransmitter substances at that time. And then when one of them got the head of the new Brookhaven National Laboratories, which was developed in Stony Brook, Long Island, they took Kotches with him, and Kotches had his own lab, and he decided he's going to work on manganese. He started with little letters of the table of elements, and started with Ma, manganese, and he measured the distribution, absorption, kinetic eliminations, and he even went to Chile to look at manganese miners who had neurological disease. He reported they had Parkinsonism, they had dystonia, these Chilean miners. He also reported that manganese reacts with phenothiazines and neuromelanin and melanin. So he got this idea that maybe Parkinson's is related somehow to melanin. And that was his idea. So he back in Brookhaven, he became aware of Carlson's work. He became aware of Hornikever's discovery of low striatal dopamine, but he wrote them off. He says, look, McGarrett didn't find any benefit. So this is not the answer. It's not dopamine deficiency. He thought it had to do with neuromelanin deficiency because there's a loss of neuromelanin in the substantia nigra. It turns out that neuromelanin is formed from dopamine. It's a condensation product from dopamine. And of course, when they lose dopamine, they lose neuromelanin. We know that today, but he didn't know that then. So he wanted to replace neuromelanin. That was his idea. So the first thing he tried was melanin stimulating hormone. He gave it to patients, Parkinson's, but it made the symptoms worse. Then he gave a precursor to the catecholamines, D-L-phenylalanine, which goes to tyrosine, which goes to dopa, goes to dopamine. But that also made the symptoms worse or had no effect. So finally he said, okay, I'll try L-Dopa. So that's how he got the L-Dopa. But what he did differently than the others, he had a federal laboratory, no charge to the patients. He did research on them. I don't think there was any IRB. There's no consent forms. They got him into the hospital free. They could stay as long as they wanted. And he started with tiny, tiny doses of L-Dopa. He didn't have L-Dopa in those days. L-Dopa was very expensive. So he started with L-Dopa, but small doses. And he kept him in the hospital, giving him a little more L-Dopa every day, higher and higher doses. He avoided the nausea, vomiting, which limited the doses from previous researchers. Finally, he hits a high enough dose, it's the magic amount, and people started getting better. So this is, it says here, he gave them up to 16 grams a day, 16 patients, and he avoided the GI side effects in most patients. And when people got a patient with dramatic improvement, 2 with moderate improvement, and when they hit 12 grams a day of L-Dopa, now that's improved to 6 grams of L-Dopa, they showed the smart benefit. So he had to use very high doses. He did have a side effect of granulocytopenia in the bone marrow in 4 patients, and he knew that it had to go to L-Dopa. He wasn't going to stay with L-Dopa, but this was the paper. This was published in the New England Journal of Medicine, February 1967, in this paper. And everybody became aware of this paper. This was a very prominent paper at that time. And then by the fall of that year, Kotz presented his work at a meeting in Montreal. The World's Fair in 1967 was held in Montreal, and Andre Barbeau there organized a 2 or 3 day symposium on, well, basically neurotransmitters and other things, but a lot of it had to do with Parkinson. He was interested in Parkinson's disease. And among them, and this is the title of the book, got published, all the papers got published, including Kotz's paper got published there. But in that, what he showed movies of his patients, and now he was using not only L-Dopa, he was using L-Dopa by this time, late 1967. And these was dramatic improvement. We're all taken aback to see this example of what it was doing. And all of us, and all these Parkinsonologists, including Mel Yard, going back to Columbia, got his group together, and they started to do double-blind studies on it. Others doing open-label studies with L-Dopa. They're all getting L-Dopa now. And from this particular symposium, and seeing those videotapes. So he published this paper. This was 2 years later. This is February 1969, 2 years after the 67 paper, just using L-Dopa alone. They got rid of the hematological side effects, and they used, of course, smaller doses. They did not still have carbidopa then. They started to use it a little later, but published this paper and in the New England Journal. But meantime, Yar came back to Columbia. He started this double-blind trial, and the first publication of double-blind trial was later. It was October '69, and he reported this with his colleagues. This is the title of his paper. Meantime, a lot of us, others guys, were working on it with open label. Harold Kalwans and Rush in Chicago, McDowell, and then at Cornell in New York. I had moved with Bud Rowland to the Penn. He hired me away from Columbia to go to Penn with him. I teamed up with Gabe Schwartz, who was the leading clinical neurologist there who had a lot of Parkinson patients. We brought his patients to the hospital. I began treating them in the hospital. Charles Markham at UCLA published, Abe Lieberman at NYU published, Andre Barbeau published, all saying the same thing. This is a dramatic effect and so forth about L-Dopa. So we had a treatment now. To sum it up, there were three main heroes. I mean, of course, everybody did all the work. You can't knock anybody down. They all tried hard. They all did. But the three main guys, Arvid Carlson, Orly Hornikavich, and George Katsias. Carlson and Hornikavich won the Wolf Prize in '79. George Katsias got the Lasker Award the same year. They published his paper in February. By the end of the year, he had won the Lasker Award for that L-Dopa paper. He was a heavy smoker. He moved to Cornell. I was talking to Dr. Boyd about this morning. Cornell hired him away from Brookhaven, but he died. He died of lung cancer from all the smoking. So he died before the Nobel Prize would be awarded in 2000, which Carlson shared with two others. Unrelated, he was only one on dopamine. And Hornig was left off. I thought the three of these people whose faces you see here should have shared the Nobel Prize, but again, it didn't happen. Katsias again had died by then. So what would happen if Katsias did not come along and show high dose the L-Dopa work? Again, neurologists had given up. Low doses were not really affected. It had to be injected. It was difficult to prepare. There was lots of doubt about any benefit. And patients were not able to tolerate high doses. They didn't have carbidopa in those days. And so we might have missed this wonderful revolutionary treatment. Superb treatment, although we'd have lots of side effects, we want a better drug. And we can also wonder, would Carlson have won the Nobel Prize if L-Dopa wasn't a success? And I leave that to us to speculate on. But I thank you very much, particularly Deepak, for inviting me. I enjoyed talking to everybody. And I'm sorry, I see I went over time. But thank you for listening. I appreciate it very much. I don't know if there's any time for questions that everybody wants to ask. Yeah. But those who lived in those days knew how exciting it was to see L-Dopa work. That was a wonderful era to live. And I always say I was the right time at the right place to take advantage of it.
That's the advantage of coming in person. You can ask the speaker live questions. And people on Zoom can also do that through chat. We'll try to field those. There are patients here and our staff and colleagues. Okay. Any question on that wonderful story?
All right, let's hope for better. Oh, Hamill.
Dr. Hamill.
Stan, thanks so much. It was just fantastic review. I was just going to make a comment. I was glad to hear your comments that Katsias probably would have won the Nobel Prize. In fact, when he was recruited to Cornell, he already had lung cancer, and he came as much to be near Sloan Kettering for his treatment. But it's really sad. And I really, because I was at Cornell at the time, and I remember when he was at Rockefeller, he was interested in trace metals and nutrition, and that's how he got into that manganese story. And it's just fascinating. He just followed his nose, so to speak. And I remember the concern about this unusual Greek fella out on Long Island who was poisoning people because their urine was turning black. But he did not give up. But what a great review. Thank you very much.
Yeah. When I was at Columbia in those early days before I moved to Penn in 1968, Roger Voisin went out to Long Island to see his patients because the 67 paper of L-Dopa came out. And then, of course, again, the November or the September symposium in Montreal. So he went out to look at his patients, and he saw these patients, and he saw the dyskinesias. He explained to Katsias what these dyskinesias were. These are choreic dyskinesias we're having. Katsias, although he did have some training, he was not a movement disorder doctor. He was not really a physician. He saw them, but he didn't know what they were really. So it was Voisin who told him about it. When I was coming up for tenure at Columbia, I had to get people to write letters for me, and I asked letters from Carlson, Ornikevich, and Katsius, and I got my tenure. So
There are some questions.
Sure, I have one question from the Zoom chat here, and we did approach over 100 people in the Zoom at one point there. The question is, why is intravenous not used at all? And I guess aside from the impracticalities of outpatient use.
Well, again, as I mentioned earlier, it's very hard to prepare intravenous. There have been certain pharmacological studies intravenous to try to infuse long-term infusion and intravenously, low doses of L-Dopa continuously to avoid the fluctuations and discontinuation. And those experiments show that the blood levels are important. And if you don't have the fluctuations in the plasma levels, you can keep a person smoothly with what we call a good on, quote on, and not have off states and dyskinetic states. This was done in one of the laboratories was Tom Chase's at NIH, and Irish Olson was a postdoc. It was the first author in those papers that came out at that time from Tom Chase's lab. So intravenous was done, again, for research only. It's not for treatment. To give IV treatment, first of all, it's not stable. L-Dopa, if you expose it to sunlight or alkali at all, it'll turn black. The skin of a banana contains dopamine. That's why it turns black after it sits around for a while. So these compounds will turn black. That's why the urine turns black. In fact, some patients in the early days of L-Dopa were noticing they were cleaning the toilet bowl with Clorox, and they had leftover urine in the toilet, and it was all black. That was converting dopa to pigment, melanin. So again, it's just too hard to prepare. Oral medicine is much easier. People tried rectal infusions. It's not absorbed through the rectum, L-Dopa. There's only a short window. L-Dopa is only absorbed in the duodenum and the upper jejunum. And the reason for that, it's not that like any amino acid can be absorbed anywhere in the intestine. The problem is it's not stable in alkali solution. It's very sensitive to the pH. So it has to be acidic or neutral to still stay alive and active. Once the pH changes, like it does in the small intestine to an alkali, it destroys the L-Dopa. That's why you have a short window when you can absorb it. And that's why it's very hard to get long-acting L-Dopa. People are trying new tricks and so forth, the way to do it. And the new drugs are coming out for that. And I don't want to go into treatment though, but the IV is too hard, and it'd be short-active anyway. It wouldn't be long sustained.
And I guess another question from the chat, and perhaps one of the burning question that we all have while we have you here with us. What do you think and conjecture will be the next big story for the treatment of Parkinson's disease since Levodopa in terms of the pharmacotherapy and anything in the pipeline that excites you the most?
Well, all the stories up to now that have been effective have been modest improvements, extending the lifespan of what an L-Dopa can do, accelerated drugs that can support L-Dopa or inhibit the enzymes that metabolize it, COMT inhibitors and so forth, MAO inhibitors. Other agents like adenosine antagonists and so forth, they can act at the dopamine system, but they're not nearly as powerful as L-Dopa. So that's why I said we're still going to be in the dopamine era, and new ways to administer L-Dopa. Some companies are trying infusing it through the skin, but you get nodules and so forth. I don't know if it's going to work at all. People have tried that with precursor drugs, and it hasn't worked. No, I think everybody's waiting. What I had in my very first slide, anticipating entering the era of neuroprotection. Most people are betting on alpha-synuclein. About 80% of all PD patients have an alpha-synucleinopathy. The others have something else. It's either mitochondrial or TDP43 or some other kinds of things destroying the nigra. But alpha-synuclein is the one that they have it causes the progression. If you can get rid of that alpha-synuclein or prevent it from forming this aggregated alpha-synuclein. Now, normally alpha-synuclein is soluble natural protein and nerve endings. But if it becomes a rogue protein, it spreads from one neuron to another. It causes the progression of disease. So there's a great effort is being made try to conquer that alpha-synuclein and get rid of it or prevent it. Whether they'll solve it that way or they'll find some other way through other genetic mechanisms, but that's where everybody's betting on the future. And so we'll have something eventually that will slow down the disease. And that's what people want, because what's happened to this disease, once it spreads, it gets to the cortex, you can get dementia, you get all kinds of other problems. And so it's not just a motor disease. That's why it's non-motor as well, because the disease spreads to other neurons. It's not just dopamine. Everybody thought it was simple dopamine, and it turns out it's not that simple. Everything's not simple in life anyway. We all know that.
So, are there any questions from audience? Otherwise, we'll probably wrap up. I'll just make 2 comments in follow up to that comment of what's the next therapy. I think as what we have learned from this wonderful story today, I think it's probably many, many years of labor with mixture of serendipity. And I think research, it's very clear if all of those postdocs and professors didn't have research, we would not be treating our patients with even levodopa today. So I think that's the most important lesson for us and patients, and to support research for Parkinson's and obviously for